Okay, so hello everyone, also a warm welcome from my side. My name is Ahmad and I'm going to present two things, FTIO and XRP. So we don't have so much time. This is why we stack both in 30 minutes. We'll start with FTIO a bit more detailed and then later look also into XRP. Okay, so FTIO, as the title here suggested, okay. So FTIO, as the title here says, is for predicting I/O phases. Okay. So what's the motivation behind that? So you all know that applications tend to alternate between compute and I/O phases, right? And compute resources are allocated exclusively, while I/O is a shared resource. Now the problem is, since it's a shared resource, it depends on what others are doing. So it has problems like variability, contention, and low utilization. Those are terms you quite often hear when you're working with I/O. Now, what you see here is a picture from the SC22 after Jack Dunger's presentation. All people basically got out and went through these two doors, basically causing contention and slowing their performance, you could say this way. And as you would guess, no one likes really contention, and this is why we try to avoid it. Now, the idea is that there are a lot of algorithms for how you can avoid contention. So, for example, there are scheduling solutions, I/O aware, batch scheduling, and the use of burst buffers, as we have seen today. The problem is that these algorithms require some kind of knowledge. For example, the number of processes doing I/O, the request size, the transfer rights, or the file access, and so on. Now, if you think from a different point of view, if you would have this information, so the temporal I/O behavior, you could answer a lot of questions. For example, is it okay to share the I/O resources? How long are the phases? Should I use burst buffers? Should I flush them or not? Can I use this information for your scheduling? So there are quite a lot of questions you could answer, but sadly the problem with that is that it's not easy to get this answer. So it's really difficult, and if you think from the phases perspective, so if you think in terms of I/O phases, it becomes even more difficult because I/O phases are really logical, either you have a phase or not, and they are composed of many small requests, right? And basically not all I/O is interesting. So some I/O is just like a minor write to a file or so. And what the problem is that if you analyze this stuff, you end up with thresholds, and these thresholds are usually application and system dependent. So this is something which is really difficult to overcome. Like you can see here in the figure, we have two phases, A and B, and we could say, okay, maybe there's just one phase, right? Because here the part is not so interesting, right? At the same time, you could say, okay, this part here is maybe not so interesting, so we could start also later and so on. So it's really difficult to do this without using system and application defined threshold. Now, what our idea was is that in HPC you often encounter applications which are periodic. So why don't focus the analysis only on the periodicity? And in fact, several studies, so I have cited here three, shows that if you have the knowledge of the application periodicity, even if it's not perfectly precise, it could lead to good contention strategies, right? And this is where FTIO basically comes in, because as the name suggests, FTIO stands for frequency techniques for I/O. And what we wanted to do is to examine the behavior of the application in the frequency domain rather than in the time domain. We wanted to describe basically the temporal behavior using just a single metric, which is the period. And we wanted also to add a few additional metrics. So once you have the period, you can further characterize with it the signal. And FTIO basically gives you also the confidence in the results, right? And we have implemented FTIO as two realizations. So we have an online version and the offline version. So the online version basically predicts during the one time of an application when the next phase is going to happen, while the offline version basically just takes a trace file, for example, a Larsen trace, and it can tell you what's the periodicity of the I/O inside it. Now, just to clarify here the terminology, when we say period of I/O, we are basically referring to the time between two consecutive I/O phases. Okay, so as you can see here, FTIO is a central component, and what you do is that you have your I/O requests, you put them in a trace file, and FTIO basically takes them, and it generates here a prediction. You can see in green a cosine wave with a frequency here, and this is basically what FTIO gives you. It gives you the frequency, and this example is 0.04 Hertz, So you take the reciprocal 1 over frequency and you end up with the period, which is 24 seconds. As I said, FTIO also gives you a confidence in the results. So it tells you here, for example, the confidence is 64%, as you can see here. We can further characterize the signal, for example, with the average byte transferred per phase. So this is just further characterization based on the period we already identified. But the big secret behind FTIO is that it treats the I/O bandwidth as a signal. So this is what we can see here. The bandwidth in the figure here is basically treated just as a signal x from t, and we apply on it several frequency techniques as we will see. Now, before we get into that, let's focus a bit on the trace file, because as I mentioned earlier, it contains per rank the bandwidth. So you basically have the bandwidth with the start and end time, as you can see here in the figure. And what FTIO does, it internally overlaps these requests so that it has an application level metric. So what we want to have is this blue one here, the application level metric. Now, in fact, it does not depend if you give it us directly or not, because FTIO can handle it independent of the level. So basically, we support all levels. So if you give us the application level bandwidth, the start time is enough. If you give us a lower bandwidth, for example, the bandwidth at the rank level or at the node level or whatever level in between, we need to have the start and the end time so that FTIO can perform this overlapping of the bandwidth, as you can see it here. Now let's dig a bit more deeper into this. As I mentioned, FTIO supports online and offline detection. Now, for the online, we have two different tools which you can use. So we have seen today that Maya monitoring proxy already. There's a second library, which is called TMIO, which you can simply just include in your C, C++ code, or you can also do an LD preload, depending on if you want to use it for online prediction. In this case, you include the file, or if you want to use it for offline detection. So there are different options on how to put basically this library inside your code. And what TMIO basically does is it's just an C++ library that uses the PMPI interface, and it just flushes the data out at certain points in your code. So you specify basically something like, here, do the I/O summary and flush out my I/O data to a trace file. This will be made soon publicly available. Now that Maya monitoring proxy is already available, you can use it also with FTIO for the online prediction. I will show in, I think, 4 slides a demonstration of that. The second option is to use the offline detection. And there you just have like a trace file sitting around. And this can be a data file, it can be a recorder folder, it can be a JSON line, a message pack file. And what you can see, it's really simple. So this is how it looks. And all you have is just the bandwidth, the start time, and the end time. And everything is calculated internally by FTIO. So let's look a bit deeper into the secrets. So how does FTIO work internally? So then, as I mentioned, you have the trace file, which is here. So you put it basically, so you import it and you perform this overlap calculation, right? And you end up with an application level bandwidth. And the idea is that you take this metric and discretize it. So you can set, for example, the sampling frequency with which you can also control which I/O is relevant for you and which is not relevant. So you can perform some kind of filtering. You end up with a discrete signal, and this discrete signal basically goes into the DFT, and we perform here the discrete Fourier analysis and end up with the power spectrum. Now we can end up also with the frequency spectrum, but with the power spectrum, we can decrease a bit the noise, okay? Because I/O tends to be very variable. So this is like the newest version of FTIO. Once you have this power spectrum, it becomes relatively easy because all you need to do is to find the frequency with the highest contribution. And for that, you can perform an outlier detection method, like using Z-score, db-scan, isolation forest, peak detection. We support basically any machine learning algorithm out there, and we can continue this list. And in the end, we just spot the frequency component with the highest amplitude or the highest power, to be precise here. And this is where FTIO basically gives you the confidence and the frequency. So this is the end. Now what you can do is that you can optionally also decide, okay, the confidence I have is quite low and I would like to have a higher confidence in my result. And if you want to do this, we have an additional method that is called autocorrelation, which runs at the same time basically, and performs autocorrelation on the already discretized signals. So we save a few computation steps, and we perform also here the autocorrelation, and you can perform the peak detection to find the frequency again and the confidence. Now, if you do this, you need to like merge the results from both frequency techniques, or from the time analysis and from the frequency technique. And this is where you can also use the scan, for example, and you end up with a single frequency and a single confidence. So this is basically the result. Okay, so this is basically the core approach of FTIO. Now, as I mentioned, FTIO can be also used in the online version, and for that you need to monitor something. So what we have is a file, so the trace file we have basically sits here. What we do is that we have a process that monitors this file. So this is the case if you use TMIO. Now, of course, when you use the Admire metric proxy, you can also use sockets. So this would be also a different option. But for now, let's say you go with the TMIO, which monitors a single file for a change. And whenever the file changes, you basically launch a new prediction process. So you go again, bring the file in FTIO, perform here the stuff we saw on the previous slide, and have the confidence and the frequency. Now there's a shared memory space between the different processes, and you can use it to perform a few additional steps. Why do we need the steps? Now, I/O tends to be very variable, right? And somehow we need to compensate for this, especially since we are doing this online. And since we are doing this online, we have basically two options. One option is to use adapting time windows. And you can imagine this like you're sliding a time window on the trace, cutting it from one side basically. So you're discarding the old result at some point because maybe the application changed its I/O behavior. The second idea is that you can also just use probability calculations with frequency intervals. So if the application at some point had a behavior and at some point it had a different one, we'll see two different intervals with different probabilities. Okay, so in the end, it depends on the use case. So if you are interested in the entire trace or only in part of it as it goes, so in which method you actually want to use. Okay, so here, to monitor the file, as I mentioned, you use TMIO, which stands for tracing MPI/IO. So this is just one option. Of course, we support also different options. Now, I put here a few pictures from FTIO because I thought it might be quite interesting to see how nice the plots are we generate. So you can see it's basically here with the command line. It's in Python coded, and you obtain a lot of stuff during its run. You can also silent it if you want to. At the middle part here, you can see, for example, the different signals composing the I/O bandwidth, which we have discretized. Here you can see, for example, the frequency in the signal, autocorrelation here, the power spectrum, the amplitude spectrum, and so on. On the right side, you can see dB scan here, and here also here with the nice circles, as you all know it. And I think this one here is isolation forest, if I'm not mistaken. So you can use different techniques to spot out the outliers. Okay, so in a nutshell, FTIO basically performs DFT and outlier detection, so several methods, and you can use autocorrelation and peak detection to gain more confidence. If you do this, the results are merged. Now, there are several properties. We don't have time to go over all of them, but basically we use the power spectrum because you can filter out noise. There are several parameters that influence the accuracy in the results. So you can, for example, use the sampling frequency to set which range of I/O is relevant for you, which I/O frequency is relevant for you, because as you know, by Nyquist, the power spectrum, for example, since it's a real signal, is limited to half of the sampling frequency, and this way you can decide which I/O is really relevant for you and which is not. As I said, we have two different methods to adapt to changing behavior, and it's an optimized Python code, which uses really true multiprocessing with different options, like using manual process creation or tools, in case you are like a bit restricted on how much processes you can perform. Now, if you perform the online version, you usually perform it not really on the cluster where the I/O is happening, and this is why also the overhead is not on the cluster side. It's more on where you want it, or where you actually execute it. And this is why you can say that the overhead is not really affecting the application behavior. Okay. Now, here's just one parameter I picked out, for example, the sampling frequency, and you can see in the left it's 10 Hertz, and the right it's 1 Hertz, and of course, if you do less sampling, you have less information, you will also fall into aliasing, but at the same time, you will ignore like the frequencies which are below half the sampling frequencies. So it really depends on what you want to capture, but with this metric, for example, you have a fine granularity on the I/O, which is really relevant for you. Okay. Now let me show you two examples. Let's first look into a detection example. So this is trace I stole from the Minds website for IO traces. So it basically is like 500 performed with 2048 ranks on the Margon 2 cluster. So we take it, put it into FTIO directly. There's no need to do anything in between, and we can obtain here a few metrics. Now let's go a bit into details here. Here you have the full trace, but compared to the previous one, we no longer have like the bytes transferred, but we have the bandwidth because we divide it basically over the time bins. The point here is that it's quite a long simulation, and if you take the entire time window here and perform on it FTIO, as you can see here, you have a really noisy signal, and FTIO will tell you, okay, it's not periodic. And if you dig a bit deeper to know why it's not periodic, you would actually see that the phases at 0 and at 45,000 transfer both 13 and 75 gigabytes respectively, and the phases at 57,000 and 85,000 transfer 30 gigabytes each. So these are the phases you see here. So these transfer 30 gigabytes, and these one here transfer the 13 here and the 75 here. Now, if you cut basically these parts, so the remaining one transfer 7 gigabytes. So if you limit this one before this phase comes here, you can see that FTIO would tell you, okay, in this range, the signal is actually periodic. So the problem is that this is the detection algorithm, and this requires a human in the loop and so on. But if this would be the online approach, it would have done the step automatically because we can move the time window during runtime. How does the online approach, so let's just conclude basically that FTIO here in the upper part tells you that the signal has a period of 4,642 and gives you a confidence of 85%. And you can basically also see why this is the case. You can see that like nearly 10% of the signal is carried out with this frequency, which has here a very high amplitude, the highest amplitude. And this amplitude lives in isolation from the rest of the signal. Okay, so now let's look into the online example. Oh, does this work? Yes, it works. So on the left side, you can see FTIO. Now I called it predictor, it's just a wrapper basically. It's monitoring a 5.8 message back. And here on the right, we have HuckIO just running. So we executed HuckIO in the loop, and it performs synchronous IO. Huck performs, you can see there are checkpoints where you see, for example, the elapsed time and how many phases there are, and what's like the period, for example. You can see here the period, 4.3 seconds. Now on the left side, you see FTIO. So in the online mode, you can see we performed the DFT with the Z-score. Here you can see the frequency that the DFT basically gave you back. Here you can see we had additionally the option to use autocorrelation to gain a bit more confidence. And here you can see that we merged the results from autocorrelation. And so this is basically the final answer you get because we used here the frequency ranges with the probability type of correlation. And as you can see, I don't know why this is so sharp. Okay, but you can also play this video back. We'll upload the slides. So it will run till it terminates. So 15 phases are over. So Hub on the right side stops, and FTIO also stops. Now, if you scroll up in Hub, you can see the period that was like 3.9, 4.0, so between 4 and 4.2. And if you look into the result from FTIO, it's like 4 and 4.17. And this was a really quick demo with only 8 ranks on my local machine because doing it on Slurm would require like recording forever. Now what you see here in the last, you can see that this is the shared memory space, which was printed out to the user at the end. And then you can see all the sample frequency, the confidence, the start time, and so on. So you can see that the start time here is always the same because we don't have an adapting time window, but you can see that the end time changes basically. Okay, so I have also a demo for the time window adaptation, but it's at the end of this slide set, but I will not present it today. Now, I promised that FTIO can do additional characterization, and this is something very interesting because we could use, for example, FTIO to detect IO bursts. And how can we do that? So for this example, we have IOR with 7,680 ranks, as you can see, and we can also see that FTIO spotted that the signal has a period of a frequency of 0.013 Hertz, which is a period of 74 seconds. Now, if I would zoom a bit here in, I would see, okay, this is the power spectrum, so the non-power spectrum. You can see there are several frequencies which are high, but there's like a pattern. And if I would zoom a bit more in, it would be quite interesting because the frequency we have here is basically multiplied by 2 is this one, and this one multiplied by 2 is this one, and so on. So they are basically all multiples of 2 of each other. And this is a direct indication that the signal has I/O bursts. Now, why is this the case? Now, let's see a small animation. So I take this signal, I put it there, I plotted it here. You can see, okay, I have a signal with 0.013 hertz, I think it was, which is the red one here. Now let me add the DC offset. So I didn't have time to explain the DC offset, but it basically shifts the signal upwards. And you can see, okay, doing this basically shifts the cosine wave to be only positive, which makes sense because we are always transferring a positive number of bytes, as you can see here. Now I'm going to add the next one, which is here. If I add it also, you can see the peaks are forming more and more, and the more I add, the higher these peaks become. And as you can see at the end, they're really close to the bursts themselves. So this way, FTIO also actually helps you to detect I/O bursts in your signal if you want. Okay, now this was quite interesting, but what do you do with it, right? It's nice to know the period, but can you show some example? So what we did is that we took this paper, which is called IO sets, and it was basically submitted at the IEEE TPDS. So our colleagues, which also worked with us on FTIO, so Francieli and Gallo, are also the authors, or are also working with us on FTIO here. And what they said is that let's recreate basically the experiment from this paper with FTIO. And what we did is that we took FTIO and we replaced this 1/period or 1/iter variable in the paper above with the frequency we have. And so FTIO is currently under review, but I uploaded it also to archive where you can check the old version, not the new one. Here you can see that there's a technical report on set10 implementation on BGFS servers. This will be made available soon, so this is still not uploaded. Now, what happens here? We have TMIO, which continuously traces an application. We have FTIO, which basically periodically gives you the frequency with the confidence. Now, there are a few more options, like having a wrapper code and where we write all the stuff. I will just skip them because they're not so relevant right now. But you can see, for example, that FTIO gives you confidence, and if this confidence is low, then we keep the all priorities with the set10 algorithm. So set10 basically gives priorities to applications, and we use the period to decide that. And basically, FTIO gives you the period. So this is how we can quickly say this. We performed the experiment on the grid 5000 FRANS infrastructure. So we had BGFS with a single OST and a single OST, right? And what we did is that we took IOR and we used the fsync option to avoid caching. We used MPI IO and the file pair process. And we also included TMIO into IOR to use FTIO. And since we wanted to have some metrics, we modified basically the timestamps so that we can see that we are good or not good, right? What we had now are 16 different IORs. Basically, 15 of them had a low frequency and 1 of them had a high frequency. The idea here is that we had for the low frequency 10 iterations, and the compute basically is a sleep for 360 seconds, and we write 320 megabytes. So basically the period is 384. While for the high frequency we had 200 iterations, as you can see here, and exactly, and 18 seconds for the compute, so a period of approximately 19.2 seconds. So in the end, we just recreated the experiment from the IEEE TPDS paper with FTIO. Now this is quite interesting because what you can see here are 3 metrics, and it's the stretch, the I/O slowdown, and the utilization. And what it basically says is the utilization shows you the time spent on compute, only on compute. I/O slowdown shows you how much the application is slowed compared by running on itself, and the geometric stretch back there shows you how much it was slowed down by others. So in the end, what we want to have is we would have like low figures or low values for these 2 here, and we would like to have here a high value, right? Now you have here our 3 experiments. To the left, you have sets10, so from the IEEE TPDS paper, where we have the priorities hard-coded. In the original version, we just have BGFS without any modification, And in the middle, we have FTIO with set 10. But you can see that FTIO plus set 10 is nearly identical or really close to what you would have obtained when you hard-coded the priority. So it shows you how accurate FTIO actually is. Also by the slowdown, we have nearly the same results. And especially at the utilization, you can see that we had a real large utilization. So if we want to speak in terms of percentages, you can see that we decreased mean stretch by 20%, decreased idle slowdown by 54%, and increased utilization by 25%, which are quite good results. Okay, so we don't have much time left for FTIO, so we just quickly go over them. FTIO has many more frequency techniques, like we can use the wavelet transformation, just skip this today, and we want to couple FTIO with extra P. I will describe this briefly in the next presentation as well, because it's about extra P, but the idea is that why don't we just plot the period or the frequency against the number of processes, so with extra P, because you already have this information. So this way you could model the phases, periodicity of the phases. So in conclusion, I'll show you FTIO, which helps you to predict the I/O behavior of an application using a single metric, namely the period, and it gives you the confidence in the results. We have offline and online realization, and there are several parameters which can be changed to influence the results. Now, it will be made very soon available on GitHub, but if you cannot wait and want to use it directly, you can just write me an email. We can find a way out. Okay, so these are some references and some acknowledgements, and that's it. So, thank you. Questions?
I don't see question online.
Okay, good. So we have enough time.
Yeah. You can continue. Yeah, simply.
Okay, second story, extra P. So same story, different points. So we want to create again models, but this time it's extra P. So here we'll see how we extended extra P in Admire to model I/O. This one is a bit of a less technical presentation because extra P already exists, and what I wanted to show you is only the extensions we have. So what's the idea here? You can see here the general structure of the Admire project, and you know the global goal of the Admire project is to balance the resources basically. And for that, a key aspect in Admire is job malleability. And you can see that we have here below, even in WP3 basically, an entire work package dedicated to malleability manager. Now this malleability manager needs to make decisions, and for that it uses the current state of the system, the jobs in the queue, user hints, and scaling performance models. And the problem is for scaling the performance, or to see how an application utilizes the resources, you need performance model which model both the compute and the I/O resources. And this is basically where XRP comes in, because XRP generates performance models. And here you can see I have put the components which do not directly interact with the performance models from XRP in gray, and the remaining components are blue. Now the data flow of the performance models is modeled in green. So you can see that basically here with the monitoring proxy, you get your traces, and then you can generate the performance models, give them to the intelligent controller, and then it's forwarded to the malleability manager. So the point here is that so far XRP was only focusing on computational and communicational aspects. But for the Admire project, we need to extend its capabilities to model I/O. But before we go into details and see how we did that, let's really briefly just look into what XRP is, okay? Probably you all have seen this slide. So when you scale your code, it can have performance surprises. And so you have, for example, here for a cluster with, for example, 4 nodes. And now you examine it and you see, okay, computation, this large, fine, it's okay. And now you want to take it to a larger system and you would expect, okay, maybe a bit larger or so. And then you look into the performance of your code, and then you see you have a huge problem with the communications. You have a huge balloon animal, as you can see here, which basically eats away all your performance with communication. Now, there are ways to get rid of that, and this is to use performance models, so you can detect which parts of your kernels do not scale good, right? And if you dig a bit deeper into that, performance models are basically formulas that express the relevant metrics as a function of one or more execution parameter. And you can imagine this like t equal to f of p, or it could be a bit more complex, like t equal to this formula. You can have it also graphical, but in the end, you have, for example, here the relevant execution parameters, for example, here the number of processes, and here you have the relevant performance metric, which can be time. So usually you're concerned with time, but the way we extend XRP here is also to model bytes and so on. Now, the idea is that if you have this one, it will be quite nice because you can see where the performance lags in your application, and you can target kernels and solve it. But to get here, it's not that easy. So let's say you want to take the manual way, so you create manually or analyze manually your code. This can be really challenging because you can have a really large code, and there can be kernels which we need to identify, and sometimes you leave some out, sometimes you take the wrong ones. But we you would end up with an incomplete coverage. What you want to end up with is a complete coverage. Exactly. So creating this model is not that easy if you perform it manually. And this is where XRP comes in, because XRP allows you to automatically generate performance models. It has a long research history and basically generates empirical performance models that predict the scaling behavior of different parts of your code. So what you can see here, for example, the different call paths and how much each one of them consumed and so on. You have here nice metrics you can slide to see at which point which function becomes critical and so on. So in the end, it helps you to identify scalability bugs. What are scalability bugs? They are basically parts of your code which application or the scaling behavior is relatively poor compared to the rest of your code. Now, XRP has been long around there, and it's also available on GitHub for free, as you can see here in the link. And if you're just interested, I need to make a bit advertisement because we have a new YouTube video. You can also check out the YouTube video, which gives you a nice overview on the functionalities of XRP. Okay, so in Admire it's a bit different because here there's no human in the loop, and we don't really want to identify scalability bugs, but we want to use it to see the scaling behavior of the application with different resources. So instead of using the GUI, as you saw, used here the programming interface of XRP, so you don't need to read this, but it's basically the programming interface of XRP. And what we wanted to do is that we wanted to continuously generate models, and the idea is that whenever new resources or new traces are available, so when the monitoring proxy just gives you new traces, you just re-invoke XRP and generate performance models once again. Now, you have, for example, here your JSON line file, JSON line, because it's quite good. It allows you to store the data, continuously append the data, basically. And what we do is that we can store in this one fine-grained data, so fine-grained I/O data, up to metrics like the total I/O time, the total transfer bytes, and so on. So whatever you basically put into this file, you will end up with a performance model. And our idea was like to put very fine-grained data and at the same time data which is also at a very high level of abstraction. So basically have everything inside it. Exactly. So you have already seen this. This is the monitoring proxy with the nice Grafana dashboard. And what you can see here is, for example, a metric which is very relevant for us, which is the I/O to total time. For example, here on a per node basis, but you can see it here also in total. You can see here the scaling performance of the different MPI functions. Exactly, and you can see the bandwidth and so on. So there are many metrics here. So these are basically the traces you'll see with the monitoring proxy. Once it terminates, you can generate a profile, you can put the profile in XRP, and you can have your performance models. At the same time, you have also the file system, like for example here with Lustro and Hub.io. And you can see we have many OSTs writing here and a lot of stuff going on. So we could basically also take this stuff and generate with it performance models. But currently we did not do it because we are a bit more centered on the application side. Okay. In the end, in Admire, we basically have 4 different ways to generate performance models with XRP. So you can use 4 different tools. You can use TMIO. So this is the one, if you remember from the FTIO presentation, which is for tracing MPI I/O. You can use Darshan, so we can just exploit this I/O trace website from the University of Mainz. We can also use the tau metric proxy, and we can also use FTIO. Now, It's basically this way that every one of these functions or every one of these tools targets a different use case. So TMIO, so this is something I did not mention today, but is more focused on asynchronous I/O. Darshan is just because everyone uses Darshan and we wanted to add a universal support. The metric proxy is very detailed, and as we have seen, it allows you to generate on the fly models, so continuous modeling. And FTIO allows you to model the I/O phases, for example, because you have the period, as we have seen on the previous slides, and with that you can model scaling behavior of the phases. But this is something we might need to extend because there's a lot of variability here. Here you can see the metric proxy in action. So you can see here we have, for example, the metric proxy with several traces, and we just put them all in a single profile in the data.json line, for example, and just generate with the performance model. So we did this here for NEC 5000, as you can see, and we have here the different API functions. So we have here the time, the hits, and the number of bytes. Currently, we just selected the number of the time, I think, exactly the time, but you can select also the number of bytes. Here on the left side, you can see IMB.io, where we did something similar. Now, we have completely described this on a blog post, so if you're interested, you can just go under admire -IO HPC, and there you can just Google this, or you can just click on this link here, and you can see the complete story in our blog post on our website. A bit of advertisement. Okay. Here you can see Darshan, again, here the Minds website with so at that time, all currently NEC 5000 traces. So at that time there were 4. I think they were from 1,000 up to 8,000 ranks or so. So this is how it looks like on the website, and we just took all of them, put them in a single file, and called XRP on that, and this is the figure we basically generated with that, as you can see here. Exactly. FTIO, as I said, is a bit problematic. We might need to extend XRP here or modify FTIO because the performance models are not so good, as you can see. But this is something we are currently looking into it until the end of the project to also predict the I/O phases. Okay, I think that's it. Thank you for your attention, and if you have questions.
Yeah.
Perfect.
I don't see any. No one from here?
There's a quick question.
Yes.
So, based on what we've seen today, we see the pipeline. We run the app, we capture information, we do modeling. What is the
So from here, yeah, it depends on which tool. So if you go with XRP, for example, tracing, profiling, the metric proxy, XRP, right? And then you put the information in the availability manager, it performs some kind of adjustment or so. This goes back to the intelligent controller, the application reconfigures and so. And this again generates new traces, which can be again put in XRP, new performance models, and so on. So there you have the feedback. For FTIO, it's a different story. FTIO would be used with the I/O scheduler. So someone is performing I/O, FTIO gets this information, give it to WP4, I think, the I/O scheduler. This one performs something, and there's no really feedback loop. It's more like a smaller I/O scheduling loop. Right? Exactly. So it basically affects on how the application I/O behavior is, which may also affect XRP, I think, and the traces, right? So you have loops in between each other, so I think it's a bit complicated. Exactly. But as I see them currently as 2 different loops.